Okay, folks. Hello. Welcome, everyone, to Session 3 of PurPL Fest. It's my great pleasure to introduce Phil Wadler. He's going to selfie.
No, I was selfieing those guys.
Oh, anyway, sorry. Phil, of course, is a man who needs no introduction, so take it away.
I hate it when people do that. Hi. Welcome back from lunch. Are there any questions? Okay. The way these talks have been going is everybody's just sort of been plowing through. And I understand the desire to do that because I've only got 45 minutes. But nonetheless, I might say something you don't understand. I hope not, but I might. If I do, please do ask a question, right? Because this should be about communication. And I hope there'll be some time at the end for people who don't have questions but who want to argue with me to argue. So I wrote this talk when I was on sabbatical in Rio de Janeiro. And Rio de Janeiro is a great place to write about programming languages because the streets are paved with lambdas. And I wrote a textbook called Programming Language Foundations in Agda. And what I want to do in my slot is tell you what I learned while writing that book. So let's see. Let's just leave that for a minute. Let's go here, see if that works. Oh, it's dead now. Okay, that's all right. I carefully set it all up, and then PDF didn't work, so I had to reboot everything. All right. How many people have heard of this book, Software Foundations? Okay, so I spent 5 years teaching from that book. And what I learned from 5 years teaching from that book is cock is well named. So you should never write a book unless you can't not write the book. That will be my only use of classical logic in this talk. And I discovered, so my first goal is just to transliterate Software Foundations to Agda. How many people have used Coq? And how many people have used Agda? Almost about the same. How many people have used Haskell? Also about the same. Agda is what Haskell wants to be when it grows up. Right? And it's not just nice because you've got dependent types, but little small things like the mix-fix syntax I really like. I think is much better than what's available in Haskell. So I really enjoyed writing this book. I wasn't an Agda expert at all when I began. I just had a few courses from Connor McBride and some of my other colleagues. But I thought, this would be so much nicer in Agda if it works. So my first goal is just to transliterate Software Foundations. And I quickly realized I don't like lots of the ways that Software Foundations tackles things, right? Benjamin Pierce, who wrote the first version and then brought on lots of colleagues, said that he was sort of he would just finish things just before the lecture. So it was written in a very tight time frame. And I think some of that shows in the structure of the book. And even though it's much more mature now, I think some of that still shows. So I felt some of this could be done more smoothly. Or I would do some of this differently. So that's what I did. So I ended up writing my own textbook in Agda. Of course, so here it is. Right? You can just go and read each of the chapters. And I had a lot of help doing this, in particular from my student, Wen Kaka. So she helped me to learn Agda, because she knew Agda. I didn't know Agda. So she helped me to learn Agda, and she put together all the software that I think the book looks quite nice, and that's all due to Wen's work. And then Jeremy has been added as a third author. Yeah, we don't still have part 3 up there, but Jeremy's done a part 3, which I think, which we'll see some of. But Jeremy's done part 3 on denotational semantics. So the book follows the same structure as Software Foundation. So the first part is learn enough Agda that you can formalize lambda calculus. And then the second part is formalize lambda calculus several different ways. And that turns out to be just enough for me to do in 1 semester at Edinburgh. It's an 11-week course, and we just get through this much material. It would be, I think, difficult to get through a bit more. And about half the course is the logical foundations, and about half is the programming language foundations. And I live in the UK, which has this tradition that all of the assessment is based on the final exam. So the students are given some work which has a nominal amount of points on it to do during term. They must do the work or else they won't learn the material. They're told that, and they do the work because it does have a nominal number of points. But then most of the score goes on the final exam, and they get a bit of practice. They get a mock exam first, and then a mock exam, and then which they get feedback on both of those, and then they get the final exam. Mock and mock, some people do really poorly. A few people ace it, but most people have significant things wrong. But they learn, and by the final exam, everybody who sat the course gets it perfect. Every now and then there's a student who didn't get it perfect. This is usually the student who thought it was a he, could get by without doing all of the coursework. And then they don't do perfect on the exam, and I'm perfectly happy with that. It turns out my school's not perfectly happy with everybody doing perfectly. That they came up last time, they said, these scores are way too high. So I've now added an optional part that they won't necessarily do perfectly on, that they're warned about in advance. So I think it's great for students, right? The whole point of having a proof assistant is there will be no errors. So I think there's a real pedagogical point to saying, I expect you to do perfectly on the exam, right? Very rarely in computing do we say to our students, we expect this to be perfect. And if you look at the software our students produce, you can see that's the lesson they absorbed. So there's a real pedagogical point, I think, in trying to be perfect. Yes?
Are any of your students producing correct Agda that is just bad style, though?
Do they do things that are bad style? Generally not. That's not been so egregious, I think, that I need to worry about that. Sometimes they don't indent it right? And I say, go and indent that. I do warn them that if it's really hard to read on the final, I might mark them down for that. I haven't needed to do that yet. Right, so anyhow, here's the textbook. And this is all produced from a literate Agda script, which is on GitHub. You can just GitHub. There it is. And again, one of the great things I discovered one of the things I learned is that if you put your textbook on GitHub, people will read it and find typos or other errors and send you pull requests to correct those typos or other errors. So this ends up being very collaborative. And then Wen wrote a script that goes through all the pull requests and automatically adds the name of any author of an accepted pull request to the acknowledgements. So there are actually quite a lot of work that's been done by people who've read the book, which is great. So I urge so one of the things I learned is GitHub is great. Write your textbook on GitHub so that other people can fix it for you. And then another thing I learned is, so here's the actual first chapter of the book. Right, begins with purple prose. The night sky holds more stars than I can count, though fewer than 5,000 are visible to the naked eye. The observable universe contains about 76 stellion stars, but the number of stars is finite, while the natural numbers are infinite. I get very excited about infinity. Infinity is really exciting, right? We all get jaded by it. But I try to remind my students how exciting it is that there's an infinite number of natural numbers, and you can define them in, where is it? There. No, not there. So it's here somewhere. Oh yeah, I talk about Brexit. Right, you need to use structural recursion. So Brexit equals Brexit is ruled out. But here's the definition of the natural numbers in Agda, right? It's just 3 lines. And you can see that this definition has 3 open ticks in front of it and 3 open ticks after it, and that's markdown for enter Agda mode. So this is actually loaded up in Agda mode in Emacs, and I can type Control-C, Control-L, and it will, oh, look what happened, right? This bit turned into color. Something much more important happened. Something much more important happened. I'll come down here to show it to you. Look, there's a little window down here. What's written inside it? Nothing, right? That's really exciting. That means that Agda processed it and generated no type errors. Right? And of course, what that means in proof terms is all the proofs are correct. Agda has accepted all the proofs. So you can execute the textbook, and the students are encouraged to do so, right? All their assignments are just in the script. I actually pull them out into a separate file that, again, they modify and execute and then submit, so that 3 or 4 chapters worth they can just submit in one file. But it's all in the textbook. You can just edit in place if you want to. And another thing I've learned from doing this, right, is that having a text, which is an executable script, is something I really like. I like it both as somebody writing and as somebody reading. Right? I mentioned there are lots of typos. They're essentially done in the Agda bits, because there can't be, because it wouldn't type check. And then if there are errors in the text, people know the Agda is correct. So if there's a mismatch between the text and the Agda, they know which one to trust, and then they know which pull request to file to fix the error in the text. So I want to strongly encourage this style of literate programming where you actually execute all of your code, whether it's Haskell or Agda or what have you. It's a much better way of getting things right. And I've read several papers written in Agda that are literate Agda scripts that I still couldn't read. And the reason why is some of it they thought, this is obvious, I won't put it in the paper. And guess what? That was the bit I couldn't follow. So fortunately, I could go and download the supplement, which did have all the Agda, and then I could understand the bit in the paper I couldn't follow. But this made me a strong advocate of not hiding anything. Just put all of the Agda in there, because if the computer can read it and understand it, maybe your reader can read it and understand it as well. It means you will not have omitted something important just on the assumption that the reader can figure it out. Okay, let's go back. So what other things did I learn from reading this book? Let's see, we need view. We need slideshow. So, of course, one thing about the book is that the title, knowing me, right, the title has to be a pun. And the pun, of course, has to be propositions as types. Right? How many people have heard of propositions as types or Curry-Howard? How many people haven't? Okay, so you're in for a treat. I will now tell you about the most important idea in computing. Right? And that is sometimes called the Curry-Howard isomorphism, sometimes called propositions as types, sometimes called the Curry-Howard-De Bruyn isomorphism, sometimes called the BHK correspondence for Breuer, Heiting, and Kolmogorov, and so on. It's important enough to have lots of different names. And the idea is very simple. It says if you write down natural deduction over here, and you write down simply typed lambda calculus over here, and you look carefully, you see they are exactly the same thing. There's a one-to-one correspondence between propositions of natural deduction and types in simply typed lambda calculus. In particular, A implies B turns into a function from A to B. And the idea is it takes What does it mean to know that A implies B? It says, give me any proof of A, and I can give you back a proof of B. So implication becomes a function space. Conjunction becomes product. What does it mean to know that A and B is true? It means I've got a proof of A and I've got a proof of B. What does it mean to know that A or B is true? That's the sum type. It says, well, either I've got a proof of A, I've labeled it as a proof of A, or I've got a proof of B, and it's labeled as a proof of B. So it's a disjunctive sum type, a disjunctive union type. And that's very important. That's a key difference between intuitionistic and classical logic, is in classical logic, if I say A or B is true, you don't know which. But in intuitionistic logic, you know exactly which one is true. And that turns out to be very useful. So that's the key idea that underlies most proof assistants, including Coq, including Agda, so that you can just use, and in dependent types, universal quantifiers turn into dependent functions, and existential quantifiers turn into dependent products. Yes, that's the right name. So everything we do is going to be executable code. And it's going to be type checking that code that convinces us there's a proof. Oh, and the correspondence is quite deep, because the correspondence says propositions correspond to types, proofs correspond to programs, and furthermore, if you simplify a proof, that looks just like executing or normalizing a program. So it's quite a deep correspondence. And it turns out to be quite broad. When I first saw it, I thought, this is just a cute trick. But then it turns out it applies to pretty much every different logic and every different interesting programming language you can name. The one thing we don't quite know how to do yet, which is really important, is concurrency and distribution. So there are some ideas about how to apply linear logic to these. So linear logic has been a great inspiration for programming languages that deal with these. But that story is far from completely told. And we need a better story about how concurrency and distribution on the programming side, what that corresponds to on the logic side. And when we get that right, I think then we will have finally a good idea about how to do in computing. Right, so here's anyhow is the textbook. And so what does this mean? It's called Programming Language Foundations in Agda. So you might think of that as, okay, these are the programming languages. There's another way to read it, which is taking language foundations in Agda. Right? Everything you do is code. So we're programming the whole time. So you can read it either way. So I didn't like the title of the book at first until I realized, oh, it's a pun. It's okay. So as I mentioned, right, you can do it in Coq, or you can do it in Agda. The first most, the first most important question is, can you actually do it in Agda? Coq is very different. Coq uses proof scripts. Proof scripts are great. It's a program that generates your program for you. And proof scripts are great if you have a lot of trivial reasoning to be done that you could just get rid of. Agda, you write out everything in painful detail. But there's a huge advantage to writing it out, which is what you write in Coq is a program that generates a program. So it's sort of the only way to understand that is to execute it. And there are tools in Coq that let you execute your proof script and see what's going on. But in Agda, you can just read the damn thing. So that's a good thing. On the other hand, maybe there are lots of fiddly cases. Right? It wasn't clear to me at all when I started, will I even be able to do this? Maybe the proofs will just get too large to read because they've got lots of fiddly small cases that you don't want to have to read about. You just want a program to generate them for you. So that was the big open question for me. And what I discovered, I'll skip over that, but what I discovered is it's fine. So the main things you want to prove about lambda calculus are progress and preservation. Here's the beginning of the proof of progress in my textbook. Here's the actual proof. And I won't go through that in detail, but you can actually sort of read this. So this says, let's see, for all M and A, if in the empty context M has type A, then progress holds for M. The definition of progress was over here, but I won't go through it. But basically you say everything either is a value, it's done, or it takes a reduction step. So if it's a variable, the answer is that can't happen, because I said here in the empty context. So there are no free variables in the empty context. That can't happen. It might be a lambda expression. We're done. It might be an application. So recursive, by induction, use progress on L. And so it will either step or be done. If it steps, then we can just take a step. If it's done, let's, again, by induction, look at progress on M. If that takes a step, then we can take a step. And if it's done, then these are both values. And then we know by the canonical forms lemma that this is value. And then we can take a step by beta reduction. I won't go through all the details, but everything fits out nicely. So this VL gets used here in the canonical form lemma, and the VM gets used here when we're showing that you can do a beta reduction step. Under call by value, you need to prove that the argument's a value, and so on. And the VL also gets used here to show that these are deterministic reduction rules. And this says, OK, you can do a step on the left of an application. This one says, if the left is a value, then you can do a step on the right. So it's a nice jigsaw puzzle. Everything fits together. I went through that very quickly. But in class, I can go through it, and the students can follow it and read it. So this is readable. That's the key point. The other thing I should point out here, which is very nice, this is part of propositions as types, is notice I referred to these as induction hypotheses, but you can also, of course, just read them as recursive calls under structural recursion. And that's the nice thing. Induction just becomes the same as recursion. So proof by induction and function definition by recursion become the same thing. So that's a very nice idea to show the students. That's also true if you use calc, but it's completely hidden. The way you use calc is you say induct on such and so when you're doing one of these programs that generates a program, and then it comes up with an induction hypothesis for you. And you never see that induction corresponds to recursion. And indeed, sometimes the induction hypothesis that the program generates for you is quite hard to understand. I would look at them and go, I don't know why that's true. Fortunately, I work at the University of Edinburgh. There are lots of calc experts there. So I'd go down the hall and speak to Brian Campbell, and I'd say, look, I don't know why this is true. And half the time he'd say, oh, it's because of such and such. I'd go, oh, yeah, OK, I could have understood that. And half the time I say, why did it give me this induction hypothesis? And Brian looks at it, and looks at it, and looks at it, and they says, no, I don't know why it gave you that either. So induction in calc can be a bit mysterious, whereas in Agda it's completely straightforward. Indeed, one thing I discovered after so I began by saying, OK, take the progress proof in Software Foundations, see if I can do it in Agda. After I did it, I discovered there was one point where induction is over terms rather than over the proof that something is correct. And the reason why is because in calc, if you try to do it over the proof that something has a type, it doesn't work out right. But if you do it over terms, it's OK. And I just did what you would naturally do, which is do it over the fact that there's a type derivation. So induct over the type derivation, not the term. And it worked fine. I was just a beginner. So there's some real advantages to using Agda, at least for simple things. So then I explain in prose the same proof that I first give in Agda. And hopefully those line up. In Software Foundations, it's similar, except first they give the proof in prose, and then here is the program that generates the program, which is the proof. So this is the calc proof script. It's indented in a similar style to what I did, but it's much harder to read. Right? So it says, right, do induction on this thing, and then do inversion, and so on. And you can learn what all these things are, and my students do, but they never understand the correspondence between induction and recursion, the correspondence between conjunction and pairs, the correspondence between disjunction and disjoint union. I think it's important to understand that. So using Agda conveys that in a much clearer way, I believe. I should mention the shortcoming. Of course, the shortcoming is if you've got the proof scripts in Coq, you can prove big things. You can prove a C compiler correct. You can prove the four-color theorem. Can people do that in Agda? I doubt they can do that yet. Maybe as Agda becomes more mature, that will come in scope, but certainly not in scope now, whereas it's well in scope for Coq. They've been doing that for years and years. Right, how much time have I got left? So I should finish and ask for questions at 2:10? 2:15? 2:15, okay. So one thing I learned is, raise your hand if you consider yourself sort of well-versed in independently typed programming and proofs. Okay, so those of you who are well-versed probably means first you define what terms are. Here's a very simple definition of terms just for the three main constructs of lambda calculus: variables, lambda terms, and application. So this is a subset of what they get in the book. In the book, the first thing they get is PCF, because this sort of doesn't work unless you have base types. So in Software Foundation, the base type is bool. In my case, the base type is PCF, so that means you get integers and you get recursion as well. So that's 4 more language constructs, I think. 3 for naturals and 1 for recursion. But anyhow, right, first you define terms, and then you give the typing rules for terms. So this says in context gamma, if x has type A, we know the term n has type B. Then in context gamma, the term lambda xn has type A to B. And all of this is executable Agda. This is part of what you get from having mix-fix syntax and using Unicode. But I have had to be careful to use my own lambda and my own arrow distinct from the Agda ones so that people don't get confused. And that gives me a chance to talk about source meta-language versus source language. So this is the way that types are first presented in the textbook. And then I go back and do it the other formulation, which is called intrinsic. And that's basically just the typing rules. You can see these read very nicely as typing rules. So now it says if in context gamma extended by A, you've got a term of type B, then when you lambda abstract that, in context gamma, you have a term of type A to B. So the typing rules become the terms. Other names for this is the extrinsic formulation is sometimes called church style. First you have terms, then you layer the types on top of them. The intrinsic style is sometimes called church style. You cannot even talk about a term unless you know its type. And the other way to say that would be terms are indexed by their types, and in fact also indexed, if they have free variables, by their context. So these are 2 different approaches. And I always thought, it's a bit of one, it's a bit of the other. They're both about equally good. Another thing about this, so this approach, we use named variables like x. Here you notice I haven't named the variables. In fact, they're referred to by De Bruijn indices. So there's several, those are actually independent choices, but in the book they go together. So here you get named variables, separate type rules. Here you get De Bruijn indices, and the type rules are built into the syntax. And those things go together, right? Because De Bruijn indices are really hard to get right. It's easy to make an error. But if your types are built into the syntax, that makes it much, much harder to make an error, because an error in your De Bruijn indice renumbering, say, comes across as a type error. Because if you use n instead of n plus 1, variable n and variable n plus 1 probably don't have the same type, and so it will show up as a type error. Or don't necessarily have the same type. So if you're trying to show well-typedness, it will come up as a type error. So it becomes easier to use De Bruijn indices without they become less error-prone because the types are built in the intrinsic formulation. Anyhow, after writing it all out, I discovered it took 2 chapters to cover extrinsic, with 451 lines of Agda code, not counting the examples, which are also Agda code. And in the intrinsic formulation, it was 275 lines. And then one day I was working out, what's the ratio? I worked it out one way, I got 1.6. I worked out the other way, I got, 0.6. Same thing after the decimal point. It's the golden ratio. So that led to my first slogan, intrinsically typed is golden. So you can do it either way, but I mostly do things intrinsically typed. Turns out much harder to do something like dependently typed systems or pure type systems or even System F intrinsically typed. Some of that's still a research issue. I will touch on that. But for the bits that I cover in the book, intrinsically typed is definitely better. I think there are a lot of advantages to it. Right. The other thing I discovered, so as I'll mention later, I work as a consultant for a crypto firm called IOHK. And one thing they did at one point is you really kind of want to get it right when you're working with crypto. So they hired Grigore Rosu, who has something called the K framework, to do some specifications for them. And in the K framework, you basically write out a bunch of rewrite rules, and then you get something that will execute those rewrites for free. Right? It's designed. It's very similar to Radix. So Radix is another system where you write out the reduction rules, and then if you write them in the right format, it will give you a reducer. So you get animation for free. So I had K envy. I wanted to get animation, and I wasn't sure how to do it. And it took me a long time to realize it's completely obvious. So how many people here realize what the completely obvious way to get animation in my textbook is? Nobody's raising their hand. Stephanie knows. Right, so it's very well known to some part of the community. I could never find a place where it was written down. Like Bob Harper knows it. He knows it really well. It's not written in his wonderful textbook. I said, am I right? Is this not in your textbook? He said, it's too obvious to put in the textbook. But it took me a long time to realize it. It took like several months. And I'll point out that other people haven't realized it either. So in software foundations, there's this normalized tactic. So there's something separate, oh dear, written in the programming language that generates programs that will normalize things for you. Well, I can't use that trick. I don't have that scripting language. I only have Agda. In this paper I found in the literature on functional big step semantics, it mentions, right, to test the semantics, one must actually use it to evaluate programs. They mention that their technique can do this, right? It gets it for free, as can many small step approaches. If you look at what they're citing, again, they're citing the K framework, that's this paper, and Radix, that's this paper. So K and Radix have it, but nobody else does, they're saying. We all have it. But we didn't realize it. Another example is the Poppelmark challenge, published quite a few years ago. Oh, good, Stephanie's in the audience, so she can answer a question for me. So challenge 2 is prove preservation and progress. Challenge 3 is animate that same system, separate challenges. But in fact, as soon as you have preservation and progress, you have animation. And it's obvious. Okay. What does progress tell us? It says either it's a value or it can take a reduction step. And we're using intuitionistic logic. So applying the proof to the term tells us which it is. And then so that says if a term is well typed, then either it's a value in a closed context, then either it's a value or it takes a reduction step. And then preservation says if a term is well typed in a context, say the empty context, if a term's well typed in the empty context and you take a step, it's still well typed with the same type. We're done! Right? That's all you need. Start with your term, start with your proof it's well typed, apply progress. Is it a value? Stop. If it's not a value, take a reduction step. Oh dear, now I need to know it's well typed. Oh, wait a minute, preservation gives me that. Rinse and repeat. That's it. That's your evaluator. And indeed, in the textbook, that's exactly how evaluation works. Oh, wait, I told you I have general recursion. Things might not terminate, but in Agda, you have to use structural recursion. Now, there's an easy trick for that, right? You just pass in a number, a natural number, here called gas, and you just count it down. And when you reach 0, you stop evaluating, very much like engines in the old racket. sorry, the old scheme. So this gives you an evaluator, and indeed, there's the evaluation that shows that the church numeral 2 applied to the successor function and 0 normalizes to 2, successor of 0. And they're much larger proofs. Like there's quite a few lines that are the proof that 2 plus 2 is equal to 4. I do that, in fact, in the book 2 ways, once with successor and 0 and once with church natural numbers. Okay. So, in fact, you do get your evaluator for free. We all have always had the evaluators for free. So the question to Stephanie, since you're an author of that paper, I'm presuming you guys didn't know that when you had 2 separate questions.
There tended to be independent questions.
Did you know that anybody using a intuitionistically-typed proof assistant could get the second one trivially from the first one?
The question is, what does it look like after? There's some UI questions that you're kind of pushing up the rugs.
Oh, right, because I asked Benjamin a few others, and they didn't say, oh, yeah, we knew that. But you at least did know it. OK, good. But I don't think I can extract that information from looking. I don't know of any. There's some blog posts and things that talk about this technique, but I've not found a published paper. Do you know of one?
I mean, nobody talked about doing that as an effective way of exploring the semantics. And that's the key thing. It's not just can you do it, but is it useful?
Good enough for my textbook, at least. More generally, I don't know. That's a good question. And indeed, I'm not sure that people have evaluated that very well yet. That would be an obvious thing to evaluate K and red X against. By the way, K's great if you're doing a reduction system. At one point, I was talking to Gregory. I said, well, we need a type system here. He said, oh, we can do that. And he wrote out some typing things. But it didn't look like typing rules. It looked like a reduction system. So it was like int plus int reduces to int. I'm going, does this make sense? And I think it does. He found a paper of Mitch Wan that did the same thing. But you have to shoehorn, right? It's a hammer, and you have to make everything look like a nail. So if you have a type system, you have to make it look like reduction rules to use K. So that's all I wanted to actually say about the textbook. But I was asked to talk about one other thing. So I mentioned that I work for IOHK, which is a cryptocurrency firm. So, right, I'm pleased to tell you there's no AI in this talk, right? Pretty much every other talk here has been about AI. I'm surprised that there aren't more talks here about crypto, because the one thing you get in crypto is smart contracts. The main model that people have of cryptocurrencies now is Bitcoin, and of smart contracts is the successor to that, which is something called Ethereum. How many people have heard of Ethereum? Yeah, quite a few of you. If you haven't, it's worth looking up. So it lets you execute smart contracts, but one thing that's happened regularly in Ethereum is somebody's made an error in their smart contract, or somebody's written a smart contract that exploits something like overflow to do a scam, so that they can devalue the currency by underflowing it, and suddenly creating more of that currency than there are grains of sand on the sea. So regularly, people on Ethereum, by accident or by scam, lose tens of millions or sometimes even hundreds of millions of dollars worth of Ether cryptocurrency. We should all be very excited about this, right? Because even though proving a program correct is expensive, this gives a use case for doing so. So one thing that's become true for one corner of the crypto world is that when you define your virtual machine, you also provide a machine-checked proof. Most people use Coq, we're using Agda, of the standard type soundness properties of your virtual machine, just to show that what you've done makes sense. So it's a business case when we defined our own virtual machine, which happens to be System F. So let me tell you a wee bit more of the story. So here's the team that's working on Plutus, and you'll recognize Michael Peyton Jones' last name. And there's some other people, like if you worked in the Agda world, I was, just from writing my textbook and looking at what was out there, I recognized Roman's name. Thompson is somebody else whose name you'll. So we've got a great team designing our own smart contract language, which is called Plutus. And of course, what do we use? We just use Haskell. So Plutus is a library for Haskell. Haskell is a big language. Verifying Haskell is quite difficult, as some of the people in this room can tell you. So what we did instead is, as with most of these crypto things like Ethereum, we compile our source language, Haskell, down to something that we call Plutus Core that runs on the actual blockchain. So the thing that runs on the blockchain is much simpler. And what you hope is once you've released something, you don't need to evolve it too often. That's called a hard fork and is to be avoided. So you'd like to design something that just stays there and is correct. So how can we design a core language that will still be good 40 years from now? Answer, use one 40 years old. So, right, I mentioned to you this correspondence between lambda calculus and natural deduction, right? Church's simply typed lambda calculus and Gerhard Gensen's natural deduction. And that's propositions as type or Curry-Howard. And I mentioned it's robust. It happens again and again. So one example is that in 1972, Jean-Yves Girard came up with System F. And in 1974, John Reynolds came up with the polymorphic lambda calculus. And it turns out, again, these are exactly the same thing. They're in one-to-one correspondence. Or indeed, they're in isomorphism because reductions of one correspond to proof simplifications of the other. So System F is around. So we basically just said, let's use higher order System F, System F omega. But we're going to use Scott encodings for our data structures rather than Church encodings, because Church encodings are inefficient. So we also need recursion. So it's just recursive types added to System F. And there's the whole syntax of it. So this is what you do for recursive types. And then you don't need recursion, because recursive types actually give you recursion. Oh, yeah, here are the recursive types, and here are the corresponding term forms for isorecursion. That, I'm sad to tell you, is not 40 years old. In fact, the only place we could find that thoroughly discussed is Derek Dreyer's thesis from 10 or 15 years ago. So you're going to tell me more sources for it. Good. No, isorecursive types plus System F. Good. Give me more sources later. But that I would like to have on a firmer foundation. But anyhow, this is what we're using. And then we hired James Chapman, whose PhD thesis was on how do you formalize things like this. So he's sort of the world expert. And he actually using my textbook as a model, because I said, here, I quickly went and modified the textbook and said, here's the beginning of the syntax of System F in intrinsic style. And then he went through and did the whole thing. Turns out doing the whole of System F in intrinsic style is a bit tough. But he got it through. And my colleague Roman liked what James did, but I won't go through that. So let me conclude. So I wrote this up, pretty much what I told you, for the Brazilian Formal Methods Symposium. I got the Best Paper Award, yay. If you want to know about propositions as types, there are many places you can look this up, one of which is my article in Communications of the ACM. And if you're younger than me, then you might prefer to have that as a video. So there's a strange loop video on the same subject. And I've gone off Twitter, but fortunately somebody showed me this nice thing that somebody wrote us about Twitter. I just proved the commutativity of multiplication in Agda and got way too much serotonin out of it. Funny face. Programming Language Foundations in Agda is, all caps, amazing. Check it out at plfa.github.io. So please do that. Thank you very much.
We have time for one or two questions.
So, on the Curry-Howard in Agda, you have this rewrite construct with
Yes.
I've never seen, is there a practical programming use for that other than propositions?
Is there so are you talking about the bits of width that are different from just defining a helper function?
I think so. I'm not sure.
Right, so width has some, it reaches places other things don't reach. This is work by my colleagues, Connor McBride and James McKenna. And I'm still a newbie at dependent types, so I can't say I've understood deeply the additional power of width. I believe I never needed to use it in the textbook. Width is just syntactically a very nice way of doing this. So you saw I used width in the proof of progress, and it's used throughout. So width is extremely useful, but your question is, could you have done it all with helper functions? And I believe the answer is no, that's not your question.
No, that's not my question. My question is, so Agda has it, it doesn't call it by the term rewrite, but the COC tactic rewrite.
Yep.
What's the programming equivalent of that? And
What's
is
the
that
programming equivalent of rewrite in Agda?
Yeah.
Agda has something called rewrite, which in fact expands into widths.
Is there a practical programming use for that, other than proving?
Oh, is there practical programming used for rewrite
Yes.
other than proving? I have not needed it for anything other than proofs. But Stephanie might be, you should turn around and ask Stephanie the same question later. She might have a better answer. Do you quickly have an answer?
I think they get erased, so they don't really do anything at runtime. But in all of these languages, deciding where you program it and you prove again is kind of a hard decision to begin with. So I can't really give you a better answer than that.
You know, if you're doing a program where you want to make sure that your vector always has length n, you could consider that a program rather than a proof. But at some point, you'll need to do rewrites to show that the length really is n. So that's an example.